This applet showing a simple resistive circuit. The blue color indicates positive voltage, and the gray color indicates ground, or movement of yellow dots indicates current, in the conventional direction. The left side of the circuit shows a voltage source providing 5 volts, and the current flows through a number of switches and resistors to the right. The amount of resistance in ohms is shown to the right of each resistor. To turn a switch on or off, just click on it. If you move the mouse over any component of the circuit, you will see a short description of that component and its current state in the lower right corner of the window. If there is only one switch closed on top and one closed on the bottom, then there is a single path through the circuit, and by Ohm's law, the current will be equal to 5V divided by the total resistance through the current path. If there are multiple current paths, you may have resistors in parallel. Resistor. A potentiometer is a 3-terminal resistor with a sliding or rotating contact that forms an adjustable voltage divider. If only 2 terminals are used, one end and the wiper, it acts as a variable resistor or rheostat. The measuring instrument called a potentiometer is essentially a voltage divider used for measuring electric potential, voltage. The component is an implementation of the same principle, hence its name. Potentiometers are commonly used to control electrical devices such as volume controls on audio equipment. Potentiometers operated by a mechanism can be used as position transducers, for example, in a joystick. Potentiometers are rarely used to directly control significant power, more than a watt, since the power dissipated in the potentiometer would be comparable to the power in the controlled load. A resistor is a passive 2-terminal electrical component that implements electrical resistance as a circuit element. In electronic circuits, resistors are used to reduce current flow, adjust signal levels, to divide voltages, bias active elements, and terminate transmission lines, among other uses. High-power resistors that can dissipate many watts of electrical power as heat, may be used as part of motor controls, in power distribution systems, or as test loads for generators. Fixed resistors have resistances that only change slightly with temperature, time, or operating voltage. Variable resistors can be used to adjust circuit elements, such as a volume control or a lamp dimmer, or as sensing devices for heat, light, humidity, force, or chemical activity. Resistors are common elements of electrical networks and electronic circuits and are ubiquitous in electronic equipment. Practical resistors as discrete components can be composed of various compounds and forms. Resistors are also implemented within integrated circuits. The electrical function of a resistor is specified by its resistance. Common commercial resistors are manufactured over a range of more than 9 orders of magnitude. The nominal value of the resistance falls within the manufacturing tolerance, indicated on the component. Electronic symbols and notation. Electronic symbol and RKM code. 2 typical schematic diagram symbols are as follows. A. Resistor. B. Rheostat, variable resistor, and C. Potentiometer. I.e. resistor symbol. The ohm symbol, omega, is the SI unit of electric. Al resistance, named after George Simon Ohm. Since resistors are specified and manufactured over a very large range of values, the derived units of milliohm, 1 m omega equals 10^3 omega, kiloohm, 1 k omega equals 103 omega, and megohm, 1 m omega equals 106 omega, are also in common usage. Milliohm, 1 m omega equals 10^3 omega, kiloohm, 1 k omega equals 103 omega, and megohm, 1 m omega equals 106 omega. Symbol, conversion, example. Milliohm, m omega, 1 m omega equals 103 omega, R0 equals 10 m omega. Ohm, omega dash. R1 equals 10 omega. Kiloohm, k omega, 1 k omega equals 103 omega, R2 equals 2 k omega. Megaohm, m omega, 1 m omega. Ohm, omega. Ohm, symbol omega, is the electrical unit of resistance. The ohm unit was named after George Simon Ohm. 1 ohmega equals 1 V/1 A equals 1 J1/1 C2. Table of resistance values of ohm. Ohmmeter is a measurement device that measures resistance. The notation to state a resistor's value in a circuit diagram varies. One common scheme is the RKM code following IEC 60062. It avoids using a decimal separator and replaces the decimal separator with a letter loosely associated with SI prefixes corresponding with the part's resistance. For example, 8K2 as part marking code, in a circuit diagram or in a bill of materials, BOM, indicates a resistor value of 8.2 k ohmega. Additional zeros imply a tighter tolerance, for example 15 M0 for 3 significant digits. When the value can be expressed without the need for a prefix, that is, multiplicator 1, an R is used instead of the decimal separator. For example, 1R2 indicates 1.2 ohmega, and 18R indicates 18 ohmega. Theory of operation. Ohm's law. The behavior of an ideal resistor is dictated by the relationship specified by Ohm's law. Ohm's law states that the voltage, V, across a resistor is proportional to the current, I, where the constant of proportionality is the resistance, R. For example, if a 200 ohm resistor is attached across the terminals of a 12-volt battery, then a current of 12/200 equals 0.06 amperes flows through that resistor. Practical resistors also have some inductance and capacitance which affect the relation between voltage and current in alternating current circuits. The ohm symbol, ohmega, is the SI unit of electrical resistance, named after George Simon Ohm. An ohm is equivalent to a volt per ampere. Since resistors are specified and manufactured over a very large range of values, the derived units of milliohm, 1 m ohmega equals 10^3 ohmega, kiloohm, 1 k ohmega equals 103 ohmega, and megohm, 1 m ohmega equals 106 ohmega, are also in common usage. Series and parallel resistors. Series and parallel circuits. The resistance of resistors connected in series is the sum of their individual resistance values. For example, the total resistance of resistors connected in parallel is the reciprocal of the sum of the reciprocals of the individual resistors. Power dissipation. At any instant, the power P, watts, consumed by a resistor of resistance R, ohms, is calculated as, where V, volts, is the voltage across the resistor and I, amps, is the current flowing through it. Using Ohm's law, the two other forms can be derived. This power is converted into heat which must be dissipated by the resistor's package before its temperature rises excessively. Resistors are rated according to their maximum power dissipation. Discrete resistors in solid-state electronic systems are typically rated as 1/10, 1/8, or 1/4 watt. They usually absorb much less than a watt of electrical power and require little attention to their power rating. Resistors required to dissipate substantial amounts of power, particularly used in power supplies, power conversion circuits, and power amplifiers, are generally referred to as power resistors. This designation is loosely applied to resistors with power ratings of 1 watt or greater. Power resistors are physically larger and may not use the preferred values, color codes, and external packages described below. If the average power dissipated by a resistor is more than its power rating, damage to the resistor may occur, permanently altering its resistance. This is distinct from the reversible change in resistance due to its temperature coefficient when it warms. Excessive power dissipation may raise the temperature of the resistor to a point where it can burn the circuit board or adjacent components, or even cause a fire. There are flame-proof resistors that fail, open circuit, before they overheat dangerously. Since poor air circulation, high altitude, or high operating temperatures may occur, resistors may be specified with higher rated dissipation than is experienced in service. All resistors have a maximum voltage rating. This may limit the power dissipation for higher resistance values. An aluminium encased power resistor rated for dissipation of 50 W when mounted on a heatsink. Known ideal properties. Practical resistors have a series inductance and a small parallel capacitance. These specifications can be important in high-frequency applications. In a low-noise amplifier or preamp, the noise characteristics of a resistor may be an issue. VZR power resistor 1.5 K omega 12 W, manufactured in 1963 in the Soviet Union. The temperature coefficient of the resistance may also be of concern in some precision applications. The unwanted inductance, excess noise, and temperature coefficient are mainly dependent on the technology used in manufacturing the resistor. They are not normally specified individually for a particular family of resistors manufactured using a particular technology. A family of discrete resistors is also characterized according to its form factor, that is, the size of the device and the position of its leads, or terminals, which is relevant in the practical manufacturing of circuits using them. Practical resistors are also specified as having a maximum power rating which must exceed the anticipated power dissipation of that resistor in a particular circuit. This is mainly of concern in power electronics applications. Resistors with higher power ratings are physically larger and may require heat sinks. In a high voltage circuit, attention must sometimes be paid to the rated maximum working voltage of the resistor. While there is no minimum working voltage for a given resistor, failure to account for a resistor's maximum rating may cause the resistor to incinerate when current is run through it. Fixed resistor. A single in-line, SIL, resistor package with 8 individual 47 ohm resistors. This package is also known as a SIP9. One end of each resistor is connected to a separate pin and the other ends are all connected together to the remaining, common, pin 1, at the end identified by the white dot. Leadments. Axial resistors with wire leads for through-hole mounting. Through-hole components typically have leads, pronounced, leaving the body axially, that is, on a line parallel with the part's longest axis. Others have leads coming off their body radially instead. Other components may be SMT, surface mount technology, while high-power resistors may have one of their leads designed into the heatsink. Carbon composition. Old-style dog bone resistors. 3 carbon composition resistors in a 1960s valve, vacuum tube, radio. Carbon composition resistors, CCR, consist of a solid cylindrical resistive element with embedded wire leads or metal end caps to which the lead wires are attached. The body of the resistor is protected with paint or plastic. Early 20th century carbon composition resistors had uninsulated bodies. The lead wires were wrapped around the ends of the resistance element rod and soldered. The completed resistor was painted for color coding of its value. The resistive element is made from a mixture of finely powdered carbon and an insulating material, usually ceramic. A resin holds the mixture together. The resistance is determined by the ratio of the fill material, the powdered ceramic, to the carbon. Higher concentrations of carbon, which is a good conductor, result in lower resistance. Carbon composition resistors were commonly used in the 1960s and earlier, but are not popular for general use now as other types have better specifications, such as tolerance, voltage dependence, and stress. Carbon composition resistors change value when stressed with overvoltages. Moreover, if internal moisture content, from exposure for some length of time to a humid environment, is significant, soldering heat creates a non-reversible change in resistance value. Carbon composition resistors have poor stability with time and were consequently factory sorted to, at best, only 5% tolerance. These resistors are non-inductive, which provides benefits when used in voltage pulse reduction and surge protection applications. Carbon composition resistors have higher capability to withstand overload relative to the component's size. Carbon composition resistors are still available, but relatively expensive. Values ranged from fractions of an ohm to 22 megohms. Due to their high price, these resistors are no longer used in most applications. However, they are used in power supplies and welding controls. They are also in demand for repair of vintage electronic equipment where authenticity is a factor. Carbon pile. A carbon pile resistor is made of a stack of carbon discs compressed between two metal contact plates. Adjusting the clamping pressure changes the resistance between the plates. These resistors are used when an adjustable load is required, for example in testing automotive batteries or radio transmitters. A carbon pile resistor can also be used as a speed control for small motors in household appliances, sewing machines, handheld mixers, with ratings up to a few hundred watts. A carbon pile resistor can be incorporated in automatic voltage regulators for generators, where the carbon pile controls the field current to maintain relatively constant voltage. The principle is also applied in the carbon microphone. Carbon film. Carbon film resistor with exposed carbon spiral, Tesla TR212 1K omega. A carbon film is deposited on an insulating substrate, and a helix is cut in it to create a long, narrow resistive path. Varying shapes, coupled with the resistivity of amorphous carbon, ranging from 500 to 800 mu omega m, can provide a wide range of resistance values. Compared to carbon composition, they feature low noise, because of the precise distribution of the pure graphite without binding. Carbon film resistors feature a power rating range of 0.125 W to 5 W at 70 degrees Celsius. Resistances available range from 1 ohm to 10 megohm. The carbon film resistor has an operating temperature range of 55 degrees C to 155 degrees Celsius. It has 200 to 600 volts maximum working voltage range. Special carbon film resistors are used in applications requiring high pulse stability. Printed carbon resistor. A carbon resistor printed directly onto the SMD pads on a PCB. Inside a 1989 vintage Psion 2 organizer. Carbon composition resistors can be printed directly onto printed circuit board, PCB, substrates as part of the PCB manufacturing process. Although this technique is more common on hybrid PCB modules, it can also be used on standard fiberglass PCBs. Tolerances are typically quite large, and can be in the order of 30%. A typical application would be non-critical pull-up resistors. Thick film. Laser-trimmed precision thin film resistor network from Fluke, used in the Keithley DMM7510 multimeter. Ceramic backed with glass hermetic seal cover. Thick film resistors became popular during the 1970s, and most SMD, surface mount device, resistors today are of this type. The resistive element of thick films is 1000 times thicker than thin films, but the principal difference is how the film is applied to the cylinder, axial resistors, or the surface, SMD resistors. Thin film resistors are made by sputtering, a method of vacuum deposition, the resistive material onto an insulating substrate. The film is then etched in a similar manner to the old, subtractive, process for making printed circuit boards, that is, the surface is coated with a photosensitive material, then covered by a pattern film, irradiated with ultraviolet light, and then the exposed photosensitive coating is developed, and underlying thin film is etched away. Thick film resistors are manufactured using screen and stencil printing processes. 8. Because the time during which the sputtering is performed can be controlled, the thickness of the thin film can be accurately controlled. The type of material is also usually different, consisting of one or more ceramic, cermet, conductors such as tantalum nitride, TAN, ruthenium oxide, RUO. Lead oxide, PBO, bismuth ruthenate, BiRUO. Nickel chromium, NiCr, or bismuth iridate, BiIRO. The resistance of both thin and thick film resistors after manufacture is not highly accurate. They are usually trimmed to an accurate value by abrasive or laser trimming. Thin film resistors are usually specified with tolerances of 1% and 5%, and with temperature coefficients of 5 to 50 ppm/K. They also have much lower noise levels, on the level of 10 to 100 times less than thick film resistors. Thick film resistors may use the same conductive ceramics, but they are mixed with sintered, powdered, glass and a carrier liquid so that the composite can be screen printed. This composite of glass and conductive ceramic, cermet, material is then fused, baked, in an oven at about 850 degrees Celsius. Thick film resistors, when first manufactured, had tolerances of 5%, but standard tolerances have improved to 2% or 1% in the last few decades. Temperature coefficients of thick film resistors are high, typically plus or minus 200 or plus or minus 250 ppm/K, a 40 Kelvin, 70 degrees Fahrenheit, temperature change can change the resistance by 1%. Thin film resistors are usually far more expensive than thick film resistors. For example, SMD thin film resistors, with 0.5% tolerances, and with 25 ppm/K temperature coefficients, when bought in full-size real quantities, are about twice the cost of 1%, 250 ppm/K thick film resistors. Metal film. A common type of axial leaded resistor today is the metal film resistor. Metal electrode leadless face, MELF, resistors often use the same technology. Metal film resistors are usually coated with nickel chromium, NICR, but might be coated with any of the cermet materials listed above for thin film resistors. Unlike thin film resistors, the material may be applied using different techniques than sputtering, though this is one of the techniques. Also, unlike thin film resistors, the resistance value is determined by cutting a helix through the coating rather than by etching. This is similar to the way carbon resistors are made. The result is a reasonable tolerance, 0.5%, 1%, or 2%, and a temperature coefficient that is generally between 50 and 100 ppm/K. Metal film resistors possess good noise characteristics and low nonlinearity due to a low voltage coefficient. Also beneficial are their tight tolerance, low temperature coefficient and long-term stability. Metal oxide film. Metal oxide film resistors are made of metal oxides, which results in a higher operating temperature and greater stability and reliability than metal film. They are used in applications with high endurance demands. Wire wound. High power wire wound resistors used for dynamic braking on an electric railway car. Such resistors may dissipate many kilowatts for an extended length of time. Types of windings in wire resistors. 1 common. 2 bifilar. 3 common on a thin former. 4 Ayrton, Perry. Wire wound resistors are commonly made by winding a metal wire, usually nichrome, around a ceramic, plastic, or fiberglass core. The ends of the wire are soldered or welded to 2 caps or rings, attached to the ends of the core. The assembly is protected with a layer of paint, molded plastic, or an enamel coating baked at high temperature. These resistors are designed to withstand unusually high temperatures of up to 450 degrees Celsius. Wire leads in low-power wire wound resistors are usually between 0.6 and 0.8 mm in diameter and tinned for ease of soldering. For higher power wire wound resistors, either a ceramic outer case or an aluminum outer case on top of an insulating layer is used. If the outer case is ceramic, such resistors are sometimes described as cement resistors, though they do not actually contain any traditional cement. The aluminum case types are designed to be attached to a heat sink to dissipate the heat. The rated power is dependent on being used with a suitable heat sink. Example: a 50 W power rated resistor overheats at a fraction of the power dissipation if not used with a heat sink. Large wire wound resistors may be rated for 1000 watts or more. Wire wound resistors are coils. They have more undesirable inductance than other types of resistor, although winding the wire in sections with alternately reverse direction can minimize inductance. Other techniques employ bifilar winding, or a flat thin former, to reduce cross-section area of the coil. For the most demanding circuits, resistors with Ayrton, Perry winding are used. Applications of wire wound resistors are similar to those of composition resistors with the exception of the high frequency. The high frequency response of wire wound resistors is substantially worse than that of a composition resistor. Foil resistor. Metal foil resistor. In 1960, Felix Zandman and Sidney J. Stein presented a development of resistor film of very high stability. The primary resistance element of a foil resistor is a chromium-nickel alloy foil several micrometers thick. Chromium-nickel alloys are characterized by having a large electrical resistance, about 58 times that of copper, a small temperature coefficient and high resistance to oxidation. Examples are chromal A and nichrome V, whose typical composition is 80 Ni and 20 Cr, with a melting point of 1420 degrees Celsius. When iron is added, the chromium-nickel alloy becomes more ductile. The nichrome and chromal C are examples of an alloy containing iron. The composition typical of nichrome is 60 Ni, 12 Cr, 26 Fe, 2 Mn, and chromal C, 64 Ni, 11 Cr, Fe 25. The melting temperature of these alloys are 1350 degrees and 1390 degrees Celsius, respectively. Since their introduction in the 1960s, foil resistors have had the best precision and stability of any resistor available. One of the important parameters of stability is the temperature coefficient of resistance, TCR. The TCR of foil resistors is extremely low, and has been further improved over the years. One range of ultra-precision foil resistors offers a TCR of 0.14 ppm/degree C, tolerance plus or minus 0.005%, long-term stability, 1 year, 25 ppm, 3 years, 50 ppm, further improved 5-fold by hermetic sealing, stability under load, 2000 hours, 0.03%, thermal EMF 0.1 μV/degree C, noise 42 dB, voltage coefficient 0.1 ppm/V, inductance 0.08 μH, capacitance 0.5 pF. The thermal stability of this type of resistor also has to do with the opposing effects of the metal's electrical resistance increasing with temperature, and being reduced by thermal expansion, leading to an increase in thickness of the foil, whose other dimensions are constrained by a ceramic substrate. Ammeter shunts. An ammeter shunt is a special type of current sensing resistor, having 4 terminals and a value in milliohms or even microohms. Current measuring instruments, by themselves, can usually accept only limited currents. To measure high currents, the current passes through the shunt across which the voltage drop is measured and interpreted as current. A typical shunt consists of 2 solid metal blocks, sometimes brass, mounted on an insulating base. Between the blocks, and soldered or brassed to them, are 1 or more strips of low temperature coefficient of resistance, TCR, manganese alloy. Large bolts threaded into the blocks make the current connections, while much smaller screws provide voltmeter connections. Shunts are rated by full-scale current, and often have a voltage drop of 50 mV at rated current. Such meters are adapted to the shunt full current rating by using an appropriately marked dial face. No change need to be made to the other parts of the meter. Resistor. In heavy-duty industrial high-current applications, a grid resistor is a large convection-cooled lattice of stamped metal alloy strips connected in rows between 2 electrodes. Such industrial-grade resistors can be as large as a refrigerator. Some designs can handle over 500 amperes of current, with a range of resistances extending lower than 0.04 ohms. They are used in applications such as dynamic braking and load banking for locomotives and trams, neutral grounding for industrial AC distribution, control loads for cranes and heavy equipment, load testing of generators and harmonic filtering for electric substations. The term grid resistor is sometimes used to describe a resistor of any type connected to the control grid of a vacuum tube. This is not a resistor technology, it is an electronic circuit topology. Special varieties: Cermet, phenolic, tantalum, water resistor, variable resistors, adjustable resistors. A resistor may have 1 or more fixed tapping points so that the resistance can be changed by moving the connecting wires to different terminals. Some wire wound power resistors have a tapping point that can slide along the resistance element, allowing a larger or smaller part of the resistance to be used. Where continuous adjustment of the resistance value during operation of equipment is required, the sliding resistance tap can be connected to a knob accessible to an operator. Such a device is called a rheostat and has two terminals. Potentiometers. Typical panel mount potentiometer. Drawing of potentiometer with case cut away, showing parts: A. Shaft, B. Stationary carbon composition resistance element, C. Phosphor bronze wiper, D. Shaft attached to wiper, E. G. Terminals connected to ends of resistance element, F. Terminal connected to wiper. An assortment of small through-hole potentiometers designed for mounting on printed circuit boards. A potentiometer, colloquially, pot, is a three-terminal resistor with a continuously adjustable tapping point controlled by rotation of a shaft or knob or by a linear slider. The name potentiometer comes from its function as an adjustable voltage divider to provide a variable potential at the terminal connected to the tapping point. Volume control in an audio device is a common application of a potentiometer. A typical low-power potentiometer, see drawing, is constructed of a flat resistance element, B, of carbon composition, metal film, or conductive plastic, with a springy phosphor bronze wiper contact, C, which moves along the surface. An alternate construction is resistance wire wound on a form, with the wiper sliding axially along the coil. These have lower resolution, since as the wiper moves the resistance changes in steps equal to the resistance of a single turn. High-resolution multi-turn potentiometers are used in precision applications. These have wire wound resistance elements typically wound on a helical mandrel, with the wiper moving on a helical track as the control is turned, making continuous contact with the wire. Some include a conductive plastic resistance coating over the wire to improve resolution. These typically offer 10 turns of their shafts to cover their full range. They are usually set with dials that include a simple turns counter and a graduated dial, and can typically achieve 3-digit resolution. Electronic analog computers use them in quantity for setting coefficients, and delayed sweep oscilloscopes of recent decades included one on their panels. Resistance decade boxes. Main article, Decade box. Resistance decade box Kurbel-Wider stand, made in former East Germany. A resistance decade box or resistor substitution box is a unit containing resistors of many values, with one or more mechanical switches which allow any one of various discrete resistances offered by the box to be dialed in. Usually the resistance is accurate to high precision, ranging from laboratory/calibration grade accuracy of 20 parts per million, to field grade at 1%. Inexpensive boxes with lesser accuracy are also available. All types offer a convenient way of selecting and quickly changing a resistance in laboratory, experimental and development work without needing to attach resistors one by one, or even stock each value. The range of resistance provided, the maximum resolution, and the accuracy characterize the box. For example, one box offers resistances from 0 to 100 megohms, maximum resolution 0.1 ohm, accuracy 0.1%. Special devices. There are various devices whose resistance changes with various quantities. The resistance of NTC thermistors exhibit a strong negative temperature coefficient, making them useful for measuring temperatures. Since their resistance can be large until they are allowed to heat up due to the passage of current, they are also commonly used to prevent excessive current surges when equipment is powered on. Similarly, the resistance of a humistor varies with humidity. One sort of photodetector, the photoresistor, has a resistance which varies with illumination. The strain gauge, invented by Edward E. Simmons and Arthur C. Ruga in 1938, is a type of resistor that changes value with applied strain. A single resistor may be used, or a pair, half bridge, or 4 resistors connected in a Wheatstone bridge configuration. The strain resistor is bonded with adhesive to an object that is subjected to mechanical strain. With the strain gauge and a filter, amplifier, and analog/digital converter, the strain on an object can be measured. A related but more recent invention uses a quantum tunneling composite to sense mechanical stress. It passes a current whose magnitude can vary by a factor of 1012 in response to changes in applied pressure. Measurement. The value of a resistor can be measured with an ohm meter, which may be one function of a multimeter. Usually, probes on the ends of test leads connect to the resistor. A simple ohm meter may apply a voltage from a battery across the unknown resistor, with an internal resistor of a known value in series, producing a current which drives a meter movement. The current, in accordance with Ohm's law, is inversely proportional to the sum of the internal resistance and the resistor being tested, resulting in an analog meter scale which is very nonlinear, calibrated from infinity to 0 ohms. A digital multimeter, using active electronics, may instead pass a specified current through the test resistance. The voltage generated across the test resistance in that case is linearly proportional to its resistance, which is measured and displayed. In either case, the low resistance ranges of the meter pass much more current through the test leads than do high resistance ranges, in order for the voltages present to be at reasonable levels, generally below 10 volts, but still measurable. Measuring low-value resistors, such as fractional ohm resistors, with acceptable accuracy requires 4 terminal connections. One pair of terminals applies a known, calibrated current to the resistor, while the other pair senses the voltage drop across the resistor. Some laboratory quality ohm meters, especially milliohm meters, and even some of the better digital multimeters sense using 4 input terminals for this purpose, which may be used with special test leads. Each of the 2 so-called Kelvin clips has a pair of jaws insulated from each other. One side of each clip applies the measuring current, while the other connections are only to sense the voltage drop. The resistance is again calculated using Ohm's law as the measured voltage divided by the applied current.